So you've got obviously an inverting amplifier. You have two oscilloscopes connected, one at the input here and one at the output here. The trace from the oscilloscope is shown here and here. So figure 1, it says that figure 1 is when it's connected across PQ. So this is your input. Figure 2, it says, is when it's connected across XY. So this is your output. Now that ties in with what you would expect, because the output is basically the inverse of what the input is. So it's inverted. You know, when this is negative, that becomes positive. When this is positive, that becomes negative. So that ties in with what we already know about inverting amplifiers. Now you're asked to calculate the voltage gain of the amplifier. In order to calculate the voltage gain of the amplifier, you don't know what RF and R1 are, but you do know what the input is, which is V1, and you do know what the output is, which is V out. Now our equation for the gain of an amplifier from standard grade is V out over V in. So we need to know what V out is and we need to know what V in is. We're given information here, 2 millivolts per division. So 2 millivolts per division for this one, there are 5 divisions there, it even gives you that. So that's going to be 10 millivolts. The output has a different amount per division, so it's 30 millivolts per division. And there are, if you count these, there are 9 divisions altogether. So it's 9 times 30, so it's 270 millivolts. So you've got the two values you need now. So it's going to be 270 divided by 10 will give you 27. Remember that the voltage gain is just a number. It's a number by which you multiply the input to get the output. So anytime you're asked for just gain on its own, it's V out divided by V in, or VO divided by V1. So that's part 1. Part 2. Calculate the RMS value of the output voltage from the amplifier. We did a question on this just the other day. VRMS is equal to V peak divided by root 2, which basically says that the peak voltage is roughly root 2 bigger than VRMS. So it's asking you for the peak value of the output voltage, so this is going to be 270 millivolts divided by root 2, 0.19. Now part 3. Suggest suitable values for RF and R1 which would produce the trace shown in figure 2. So the trace shown in figure 2 is 27 times bigger than this. So you need resistors that make that happen. So if V out divided by V in is equal to 27 as it is in part 1, then RF divided by R1 must also be equal to that. So you're just looking for two resistors that are a factor of 27 apart. The easiest way to do it is to just use the same values pretty much as you've got here, except make it into something realistic like 10 kiloohms and 270 kiloohms. That satisfies the condition there. Now you don't need to put negative values in for this resistance here, that's not necessary. This is just to tell you that it's going to make the output negative if the input is positive and vice versa. So if this is 27, then that's got to be 27 as well. The ratio of RF to R1 has got to also be 27. We talked about this, that these resistors are what determine the gain that the amplifier has. Right, second part. So it now switches to a monitoring circuit with a differential amplifier. So B, part 1. When the temperature of the thermistor is 23 degrees, the reading on the digital voltmeter is 0. So that's here. That reading is 0. What is the value of the potential difference between X and Y? Well, a differential amplifier, all it does is it takes the difference between V2 and V1 and amplifies that. So if the output is 0, then the voltage difference must be 0. And the voltage difference here, as we've just talked about, is determined by what the potential difference across the Wheatstone bridge is. So if this potential difference is 0, then that's going to be 0. So therefore, the value of the potential difference between X and Y must be equal to 0. Part 2. When the temperature of the thermistor is 26 degrees, the reading on the digital voltmeter is negative 0.18. What now is the value of potential difference between X and Y? Anytime you're asked this, write down your equation for the differential amplifier. What it's asking you there is potential difference between X and Y, which is the same as V2 minus V1. So V out is negative 0.18. RF is here, that's 1 megohm. So 1 times 10 to the 6. R1 is here, 100 kiloohms. And it's V2 minus V1 that we're really trying to calculate. So we pop our values into that. Negative 0.18 equal to 1 times 10 to the power 6 over 100 times 10 to the power 3 multiplied by V2 minus V1. So negative 0.18 is equal to 10 V2 minus V1. So V2 minus V1 must be equal to negative 0.018 volts. You've got a negative voltage coming out of here. Remember, all that's doing is amplifying the difference. So it must be amplifying a negative voltage in order to get a negative voltage out the other side. So anytime you're asked for, what is the potential difference between X and Y, or between the 2 points in the Wheatstone bridge, it's just the same as saying V2 minus V1. So you won't always necessarily have to calculate just one of these voltages on its own. You might have to calculate that whole term, which is effectively just what the reading on here would be. Part 3. State what happens to the reading on the digital voltmeter when the temperature of the thermistor falls to 20 degrees. Well, 26 degrees, this 23 degrees, in fact, we'll go back to that, 0 volts at 23 degrees, so it's balanced at that point in time. Negative 0.18 at 26 degrees. If you remember back to resistance against voltage, in direct proportion. So if this is 3 degrees under what it is at balance, then we're going to get the opposite of that. So if this here is negative 0.18, then it can be the same here for that value of resistance. That could be temperature, it's really the same thing. So we're looking at plus 0.18 volts. So the reading would increase. The reading increases because of the direct proportion of the change in resistance to the change in voltage. You would need to obviously explain that a bit more, but I'm not going to write it.